Hi, in this video, I'll provide a detailed presentation of our ICLR 2025 paper on exploring local memorization in diffusion models via right-handing attention. I hope you find it both helpful and interesting. From the title, you probably recognize diffusion models. They've become one of the most popular types of generative models today, but this raises a few key questions. What exactly is memorization in diffusion models? What do we mean by local memorization? Finally, what is bright-ending attention and how it can help us to explore such an issue of local memorization? Please keep these questions in mind and we'll discover them one by one in the following slides. Okay, so question one, what is memorization in diffusion models? In short, is a major limitation of diffusion models. It refers to the fact that pre-trained diffusion models can actually memorize images from their training set and later reproduce them during inference. Let's take a look at some examples. These images come from the line dataset, which is part of Stable Diffusion's training set. Now compare them with these generated images from Stable Diffusion. As you can see, they are identical to the training images, clear evidence of memorization. So why does memorization matter? First of all, it raises privacy concerns and legitimate risks. Imagine that there are some copyrighted images in the training set, such as the faces of certain high-profile people or some artworks by living artists. Well, Van Gogh is an exception. You can safely play with it and generate Van Gogh-style images without violating any copyright laws. Since Van Gogh has passed away for over 130 years, while the copyright laws tends to only cover a person's lifetime plus 70 years. However, there are tons of active artists still out there, alive, and they'll fight for it if someone simply used Stable Diffusion to generate their artworks. This isn't hypothetical. There have been real lawsuits filed against companies like Stability AI, Midjourney, and Runway AI. Artists have described Stable Diffusion as a 21st century college tool, remixing copyrighted works from the countless images used in this training data. Two key factors make this even more concerning. First, these methods are open source and deliver state-of-the-art performance, which makes them incredibly popular. Their outputs are now everywhere, meaning both developers and users are constantly at risk of violating copyright laws. Second, the training dataset are massive, often contains billions of text-image pairs, so it's just not realistic to manually filter out all copyrighted material. A much more scalable solution is to design algorithms that can proactively prevent the model from memorizing and reproducing training data. And that's exactly what a growing body of research is now aiming to achieve. But beyond legal risks, there is another reason that this matters: creativity. So generative models are supposed to create new content, not just regurgitate what they've seen. As a research student, I've often had reviewers telling me that your paper is not novel, so I recommend rejection. So now it's our turn to say that, hey, Stable Diffusion, I know you're impressive, but if you keep copying, you're not novel either. So I recommend rejection of your outputs. I'm sure we all agree by now that memorization is a serious concern. So let's move on to the next question. What exactly is local memorization? You might have noticed that we say diffusion models can exhibit both global and local memorization, but what do we mean by that? It's actually quite simple. Global memorization refers to the cases where the generated images is an exact copy of a training image, just like the example we saw earlier. But memorization doesn't always involve the whole image. Sometimes only a part of the training image is memorized. This could be the foreground, the background, or even a specific object. That's what we refer to as local memorization. And it's worth noting that global memorization is essentially just a special case of local memorization, where the memorized region happens to cover the entire image. After introducing the definitions and motivations of memorization in diffusion models, let's dive into the research gaps we have observed that motivates the core designs in this paper. In response to the memorization issue, various methods have been proposed to evaluate, detect, and mitigate memorization by several interesting papers. They have really advanced the field through the effective strategies they have designed. This allows us to build on their work and further advance the field. A research gap we observed is that all existing studies on memorization in diffusion models are from a global perspective, comparing the entire generated images to training images. However, the existing evaluation, detection, and mitigation strategies from such a global perspective can be easily tricked in local memorization scenarios by introducing diversity in the non-memorized regions, resulting in many false negatives. Don't worry about this if it's still not clear to you yet. Let's go through each of the strategies from evaluation strategies to detection to mitigation strategies to see how and why they underperform in local memorization cases. Let's now talk about how memorization is typically evaluated. One widely adopted method is called self-supervised copy detection or SSCD. It works by extracting embeddings from both the generated image and the training image. Then it computes the cosine similarity between these embeddings. This value is referred to as the SSCD score, which serves as a standard way to quantify how similar the two images are. In general, an SSCD score above 0.5 is considered a sign of memorization. Let's look at a few concrete examples. These images here are from the training set, and these are the corresponding images generated by Stable Diffusion. As you can see, all of them have an SSCD score above 0.5, so they are classified as memorized. Manual inspection confirms this, so they are indeed memorized, but more specifically, they are local memorization cases, since only parts of the original images are being copied. Now let's take a look at this next row. These are also generated from Stable Diffusion, but this time all of their scores are below 0.5, meaning the method classifies them as non-memorized. However, if we look closely, we see that they actually also local memorization cases. They are nearly identical to the previous row in the memorized regions. The only differences are in the non-memorized regions, like the patterns on the suitcase or the pillow. This exposes a key weakness in the current evaluation approach. It's not reliable for detecting local memorization. Why? Because the SSCD score takes a global perspective. It compares the entire generated images to the entire training image. So if the non-memorized parts of the image are varied, even if the memorized regions is identical, it can drive the similarity score down and result in a false negative. In short, SSCD isn't robust to variations outside of the memorized area. A generated image can copy just one small region while changing everything else, and the matrix might completely miss it. This highlights the need for a more localized evaluation method. Now let's look at one of the most commonly used detection strategies. A popular method relies on magnitude of the difference between two outputs of the denoising model, one conditioned on the text prompt and one unconditioned. This difference is used as a signal for memorization. Don't worry about the exact equation just yet. We'll walk through it in the next few slides. For now, just keep in mind, the larger the magnitude, the higher the risk of memorization. However, this approach is much less effective for local memorization compared to global. And the reason is similar to what we just discussed. It takes a global view of the image, computing the magnitude across the entire output, without focusing specifically on the locally memorized regions. Here we show a distribution plot of the magnitude values during its first denoising step, that is when time step t equals 0, for three different scenarios: global memorization, local memorization, and non-memorization. As you can see, local memorization cases have smaller magnitudes than global ones. In fact, their values are much closer to the non-memorized cases, making them harder to distinguish. This again highlights a key limitation of current detection methods. They fall short when it comes to identifying local memorization. While the previous density plot only showed the distribution of magnitude values at the first inference step, here we go a step further. We plot the entire trajectory of magnitude values across all denoising steps. using one representative example each for global memorization, local memorization, and non-memorization. Let's start with the dashed lines. These represent the magnitude values computed using the standard equation we introduced earlier. And again, we see the same trend. Local memorization cases consistently show lower magnitudes than global ones, making them harder to distinguish from non-memorized cases. But here's the exciting part. This plot also contains a bit of a spoiler. The solid lines represent our refined magnitude, which is specifically designed to take a local perspective rather than a global one. As you can see, the refined matrix significantly boosts the magnitude values for local memorization cases, while leaving the global and non-memorized cases largely unchanged. This makes local memorization much easier to detect. We'll explain in more detail later in this presentation. Now let's take a look at the current mitigation strategy and how it is tightly coupled with the detection method we just discussed. Specifically, the mitigation approach uses the detection magnitude as a loss function. It computes the gradient of this magnitude with respect to the user prompt embedding, denoted as EP. The gradient is then used to update the embedding through backpropagation. Once optimized, the new prompt embedding is used to condition Stable Diffusion, guiding it to produce less memorized outputs. In this way, the model effectively mitigates memorization. However, this mitigation process is only triggered when the detection strategy successfully identifies a memorization cases. That is, when the magnitude exceeds a certain predefined threshold. And here lies the core issue. Because the mitigation strategy relies so heavily on this detection signal that we already know to struggle with local memorization, it also ends up underperforming in those cases. In other words, if the detector misses local memorization, the mitigation never even get a chance to kick in. Building on our earlier recognition of the limitation of how local memorization is measured, detected, and mitigated, we'd like to emphasize a broader point. Local memorization is not just a niche concern. It's actually more generalized and practical notion of memorization than global memorization. And here's why. First, unmemorized regions pose no legal or ethical risk and can be safely ignored. In contrast, even a small locally memorized region, say a copyrighted logo, a face, or a distinctive artist element, can result in serious legal consequences. Second, local memorization encompasses global memorization. In fact, global memorization is simply a special case of the local memorization. So by addressing local memorization, we naturally cover both. In this way, shifting the focus to local memorization doesn't diminish existing work on global memorization. It actually builds on it and extends its scope. So our core proposal is this. Future investigations into memorization should adopt a local perspective. That means designing improved strategies that concentrate only on the regions that are actually memorized, because those are the parts that matter. The rest of the image which isn't memorized presents no risk and should be ignored. Motivated by this shift towards localization, the natural next question becomes, how can we investigate local memorization? Ideally, we'd want to extract a local memorization mask, a mask that highlights the specific regions of the image that are being memorized. If we have that, we could revisit and revise all existing strategies, including the evaluation, detection, and mitigation strategies, and redesigning them from a local perspective. So how can we obtain such a local memorization mask? A straightforward idea would be to compare each generated images to its closest training image and look for overlapping regions. But this approach has some serious limitations. First, it defeats the purpose. Using the training data to detect memorization raises privacy concerns. It assumes the user has access to the original training set, which isn't always the case. Second, it's computationally expensive. Finding the nearest neighbor in massive datasets like Lion is extremely costly and make the entire process impractical, especially when we want to use these masks for real-time detection or mitigation. So we take a different route. We aim to extract these local memorization masks without using any training data at all. Instead, we rely solely on the pre-trained model itself and its internal memory to review patterns of memorization. So recent studies have shown that text conditioning is a key driver of memorization, so we decided to use the text prompts as the basis for extracting our memorization masks. This led us to focus on the cross-attention mechanism in the UNet architecture of diffusion models. Cross-attention links individual text tokens to specific regions in the generated images. And our intuition is this. When the model memorizes something due to overfitting, its attention behaves differently compared to when it generalizes. This memorized generations follows a fixed, rigid denoising trajectory, which we can track and distinguish from the non-memorized outputs. Before we introduce our new observation, what we call the bright ending phenomenon, let's briefly recap how cross-attention works in Stable Diffusion. Cross-attention appears in 16 layers of Stable Diffusion's UNet, and it plays a key role, which is injecting conditioning information like text prompts into the denoising process. Essentially, it helps the model decide how much attention to pay to each text token, so that the semantic meaning of the prompt can effectively guide the image generation. Cross-attention weights are computed using the scale dot product between the query and the key. In this context, the query comes from the latent representation of the image, while the key comes from the text conditioning. This operation essentially determines how strongly each part of the image should attend to each token in the prompt. To identify distinguishing memorization patterns, we visualize the cross-attention weights. Specifically, we average the cross-attention weights from the first two downsampling layers of the UNet during the final denoising step. This gave us a clearer picture of where the model is focusing its attention at the very end of the generation process. In doing so, we discover an interesting and consistent phenomenon in pre-trained diffusion models. During the final denoising step, the end of text token usually produces a dark cross-attention map. You can see this in the last row of the figure on the slide, under the end of text column. This dark map usually contains only faint, low attention outlines or scattered points. Since the end token is meant to summarize the full prompts, this suggests that near the end of denoising, when the image is almost clean, the model shifts its focuses away from high-level semantics and instead hones in on fine-grained visual details. However, in memorized cases, we observe a clear anomaly. The end token's attention map become bright. This unusually high cross-attention activation is what we call the bright ending phenomenon, or BE. Rather than just focusing on fine details, the model now attends to causal structures across broader image patches, even at the final denoising step. This suggests that the model is still strongly relying on the text conditioning, showing signs of overfitting, a hallmark of memorization. In cases of global memorization, the entire images light up. In contrast, for local memorization, only the memorized regions show the bright activation, creating a localized bright ending effect. And there it is. The bright ending anomaly effectively acts as an automatic memorization mask. It serves as a global mask when the whole image is memorized, and as a local mask when only parts of the image is copied. This gives us a direct and training data-free signal of where memorization is occurring, right from the model's own attention patterns. To further validate our bright ending observation, we conducted a large-scale experiment. We began by selecting 300 prompts that are known to trigger memorization in Stable Diffusion, sourced from a widely used benchmark. For each of these prompts, we generated 16 images. We then selected another 300 non-memorized prompts from datasets like Lexica, Lion, Coco, and randomly sampled captions. And again, generated 16 images per prompt. This gave us a total of 4,800 generated images for both memorized and non-memorized cases. Within the memorized group, we further classified the images into global and local memorization. We then visualized the distribution of end-of-text token attention scores at the final denoising step using a box plot across all images. The results were striking. Non-memorized cases consistently showed attention scores close to 0. In contrast, memorized cases had significantly higher attention scores. And importantly, global memorization cases show the highest score overall, likely due to the model memorizing large regions of the image compared to local cases. This slide presents additional examples of the memorization masks extracted using our bright-ending attention method, covering both local and global memorization cases. The success of bright-ending in identifying localized memorized regions opens up exciting opportunities to improve existing strategies for evaluation, detection, and mitigation. By integrating the BE-generated local mask into these workflows, we allow current methods to adopt a local perspective, helping to close the performance gap we've seen in handling local memorization. Let's start by looking at how this benefits the detection strategy. To quickly recap, in unconditional generation, the denoiser's objective is to minimize the expected squared norm between the predicted noise and the ground truth noise from the forward diffusion process. In the conditional case, when text prompts are used, we compute the same square difference but use the text-conditioned noise prediction instead. Now here's where bright-ending comes in. The bright-ending attention map naturally functions as a memorization mask. We start by computing the differences between the text-conditional and unconditional noise predictions across the entire latent space. Then we apply the BE mask through the element-wise multiplication to localize this signal, focusing only on regions at risk of memorization. We follow this by normalization to ensure consistency across different mask scales. Finally, we apply a threshold, like 2.0, to this localized detection signal, which we refer to as LD. If the value is above the threshold, it's flagged as a positive detection. Otherwise, it's treated as a non-memorized case. Next, let's talk about how bright-ending also improves the mitigation strategy. As we discussed earlier, the standard mitigation methods relies on the magnitude-based detection signal. Specifically, it works in two steps. First, it performs prompt engineering by optimizing the embedding of the user's input prompt, using the detection signal as the loss function for gradient computation. Second, it only triggers this optimization process when the detection signal exceeds a predefined threshold. Here again, by incorporating the bright-ending derived local mask, we allow the mitigation strategy to adopt a local perspective, leading to significant improvements. First, by replacing the old global magnitude with the localized detection signal as the loss function, we provide much stronger and more relevant gradient information during backpropagation. This results in more effective prompt optimization, especially for local memorization cases. Second, because the local detection signal is a better signal for detecting local memorization, the mitigation strategy can be triggered more accurately. As a result, the localized mitigation strategy is more effective in reducing memorized generations, particularly in the challenging local memorization scenarios where previous methods struggled. Finally, let's look at how bright-ending can enhance the evaluation strategy. As mentioned earlier, the current standard for evaluating memorization is the self-supervised copy detection method, or we call it the SSCD. Earlier methods also explored simpler alternatives, such as the Euclidean distance. As a first step towards improving robustness, we compare SSCD and Euclidean distance into a single matrix, hoping to compensate for SSCD's limitations in detecting local memorization. This helps to some extent, but there's still a fundamental issue. The entire comparison is done from a global perspective as well, evaluating similarity between the whole images. To address this, we propose incorporating the bright-ending attention mask into the evaluation matrix. By doing so, we refine the score into a localized evaluation matrix, focusing only on the regions identified by the bright-ending mask as potentially memorized. To wrap up, our localized strategies were specifically designed to improve performance on local memorization, and that's exactly what we see in the results. Across detection, mitigation, and evaluation tasks, our localized methods achieved significant gains for local memorization cases, we're still maintaining comparable performance for global memorization scenarios. Let's dive into the experimental results, starting from detection performance. This table shows the detection performance across three commonly used matrices, AUC and true positive rate at 1% of false positive rate, which is denoted as T at 1% F, and the last one is the F1 score. We evaluate under three settings based on how the detection magnitude is computed, using only the first inference step, averaging over the first 10 steps, and averaging across all 50 inference steps. As you can see, our localized detection strategy consistently outperforms the baseline across all matrices for local memorization. And importantly, it maintains comparable performance for global memorization cases. Now let's take a look at the results for mitigation performance. This figure illustrates the privacy-utility trade-off achieved by our localized mitigation strategy. We evaluate the generations using both global and local similarity matrix and compare our results against those from the baseline mitigation strategy, which was developed from a global perspective. Let's focus on the local memorization results first. There are two key takeaways. First, for the same level of privacy, measured by the similarity score on the vertical axis, we achieve better utility, as shown by a higher CLIP score on the horizontal axis. Second, for the same level of utility, our approach achieves better privacy with lower similarity scores. Visually, you can see that our curve consistently lies in the bottom right relative to the baseline, indicating a superior privacy-utility trade-off for local memorization. For global memorization, our performance remained comparable to the baseline, and that makes sense. The bright ending mask was specifically designed to target local memorization, so we wouldn't expect it to interfere with global mitigation. This table shows the F1 score of three different evaluation metrics. For the global memorization cases, which are relatively easier, all methods correctly identify memorized and non-memorized generations, achieving perfect F1 scores. However, for local memorization, we start to see differences. Combining SSCD with Euclidean distance can somewhat help mitigate SSCD's performance gap. But most importantly, when we redesign this combined matrix using the bright endings local memorization mask, turning this into a localized evaluation matrix, we observe a further improved F1 score. In summary, our results shows that by incorporating the localization insight, all of our localized strategies for detection, mitigation, and evaluation achieve enhanced performance and set a new state-of-the-art in handling memorization in diffusion models. It is also important to highlight that the success of these strategies serves as an extrinsic validation of the bright ending attention map. It confirms the bright ending's effectiveness in automatically extracting local memorization masks, which we believe will be a valuable asset for future research on local memorization. Thanks so much for watching. Please check out our paper for more details.